Welcome to today's deep dive. We are really glad you could join us. I want you to start by just looking at the hardware around you right now.
Yeah, your laptop, maybe a desktop rig sitting quietly in the corner of your office.
Exactly. For the vast majority of its operational life, the processing architecture inside that machine is essentially dormant.
Right. The silicon is powered, the OS is doing its background tasks, but the actual compute capacity, it's wildly underutilized.
Right. Now consider a scenario where the latent processing power of your specific machine, along with, millions of others, is actively aggregated to train physical, autonomous robots navigating the real world.
It sounds like science fiction.
It really does. Furthermore, imagine a framework where your hardware's contribution to this massive global task is autonomously compensated, like via decentralized cryptographic ledger. You get paid in crypto for what your dormant PC is doing.
And this is the exact architectural proposition we are examining today. It's a radical departure from the traditional hyperscaler model.
Oh, absolutely.
We are looking at a paradigm shift where edge compute is not just retrieving data from a server somewhere, but actively participating in the heavy lifting of artificial intelligence training and inference.
So today we are analyzing a single, very dense source for our deep dive. It's a case study published by the Pi Network on March 5, 2026.
Titled The Pi Node Decentralized Computing Case Study.
Right. And our mission for this deep dive is to deconstruct how a massive, globally decentralized network of everyday consumer-grade hardware is attempting to address the really severe computing bottleneck inherent in the current AI expansion.
And we are going to specifically examine a proof of concept pipeline involving a robotics company called OpenMind.
Okay, let's unpack this.
Yeah.
Because we have a highly technical document to parse here, and the implications for distributed systems architecture are, well, they're substantial.
Very much so. As we dissect the Pi Network's claims, we are fundamentally looking at the intersection of three things: blockchain consensus mechanisms, global AI infrastructure, and verifiable human participation. This case study proposes a structural alternative to the monolithic data centers that currently dominate the entire AI landscape.
So to understand the viability of this proposed alternative, I think we have to start by analyzing the specific bottleneck it claims to solve.
Yeah, that's a good place to start.
Section 1 of our discussion centers on what we can call the Great AI Compute Crunch. The source material frames the current era of artificial intelligence as being constrained by two intersecting vectors.
The physical limitations of centralized computing and the exponential demand for compute cycles.
Right, the cycles required to train and run increasingly complex multimodal AI models. Society, and the tech sector specifically, is hitting a massive wall when it comes to raw computational throughput.
Because the demand curve for AI compute is not linear, it is geometric.
It's exploding.
Exactly. But the infrastructure supporting that demand is currently bound by the strict physical realities of centralized hyperscale data centers.
Yeah, the case study points to some very specific structural constraints we need to analyze. It highlights energy concentration, data center constraints, and algorithmic friction points like catastrophic forgetting and global state bottlenecks.
So let's focus on those physical constraints first.
Yeah, let's do that. Because when the text discusses energy concentration, what are we really talking about?
We are talking about the macroeconomic and thermodynamic realities of modern AI infrastructure. Building a state-of-the-art facility to house tens of thousands of GPUs isn't just about the cost of the silicon itself.
Right. Buying the chips is only half the battle.
Less than half, really. It is about the localized power draw. You are pulling hundreds of megawatts from a regional power grid.
Just massive amounts of electricity.
Precisely the issue. Energy concentration refers to the localized density of power required. We are seeing major tech hubs right now facing severe grid instability because you cannot simply drop a gigawatt-scale data center into an existing municipal power infrastructure.
You'd dim the lights for the whole city.
You'd crash the grid, you require dedicated substations, you need massive cooling infrastructure to manage the thermal output of high-density server racks, and extensive water resources just for that cooling.
So the geographic locations that can even support this level of localized energy concentration while also providing the necessary fiber optic backbones for the internet connection, they're finite.
Highly finite. The centralized model inherently limits horizontal scaling because you run out of physical locations capable of sustaining that much localized power and heat dissipation.
It makes me think of an analogy. Centralized computing right now is like a massive, congested superhighway where all the traffic the data has to pass through one giant toll booth.
That's a great way to picture it.
Right, but decentralized computing, which we'll get to, is like millions of backroads working together seamlessly.
Yeah.
No single toll booth to jam everything up.
Exactly. So the physical architecture is bottlenecking at that toll booth, but the case study also delves into the software architecture of centralized AI.
Yeah, it specifically mentions global state bottlenecks.
Right.
In distributed systems engineering, maintaining a global state across a massive cluster can severely degrade performance. How does the text frame this in the context of AI training?
Okay, so in a centralized training paradigm, particularly with massive parameter models, you have a master node, or a highly coupled cluster that maintains the definitive state of the model's weights.
The actual brain of the AI.
Yes, the global state. As thousands of processing units compute gradients based on the training data, they must continuously synchronize with this global state to update the model.
So they all have to check back in with the boss.
Exactly. The bottleneck occurs because this synchronization is often synchronous or semi-synchronous. The system experiences severe latency as it waits for individual nodes to finish computing, report back, and for the global ledger of weights to resolve and update before the very next iteration can begin.
So the overhead of managing this single source of truth across tens of thousands of concurrent operations just creates a hard ceiling on computational efficiency.
It creates a scenario where adding more GPUs to a cluster yields diminishing returns because the network fabric and the global state management simply cannot handle the synchronization traffic.
Wow. And the text also points to something called catastrophic forgetting.
Yes, a known issue in sequential learning for neural networks.
Right. So if a model is trained in a centralized, monolithic way, when it attempts to learn a radically new set of tasks or adapt to a new physical environment,
The rapid updating of its centralized weights can actually overwrite the representations it learned previously.
it just deletes the old stuff to make room for the new stuff.
That is the core of catastrophic forgetting. Because all the knowledge is stored in a single, highly coupled neural architecture, shifting the optimization landscape to accommodate new data often destroys the local minima that represented older, established knowledge.
So it forgets how to walk because it's trying to learn how to run.
In a sense, yes. What's fascinating here is that the Pi network case study posits that heavily centralized architectures actually exacerbate these issues.
Okay, how so?
The text suggests that relying entirely on tightly coupled data centers creates vulnerabilities not just in hardware failure, but in the algorithmic flexibility of the AI itself.
Ah, I see. It implies that a decentralized, highly distributed approach might naturally lend itself to compartmentalized learning.
Precisely, mitigating things like catastrophic forgetting by allowing different nodes to maintain specialized submodels or states.
Okay, so if the centralized model is hitting a physical wall regarding power grids and a software wall regarding synchronization latency,
The alternative has to involve utilizing resources that are already deployed but idle.
which is the fundamental premise of edge computing.
Yes. But the challenge has always been orchestration. How do you reliably harness millions of disparate, untrusted consumer devices with varying uptime, varying latency, and completely different processing power?
And that brings us perfectly to section 2 of our analysis, the Pi network solution. The text positions this as a sleeping giant of compute, a massive pool of unused computing capacity.
And the case study presents some very aggressive metrics here.
They claim a distributed network architecture consisting of over 421,000 nodes globally.
Which represents an aggregate of over 1 million CTUs.
Here's where it gets really interesting, though.
Yeah.
The scale of that node count is significant, right? For context, typical distributed computing projects or decentralized blockchains consider a few thousand active nodes to be a highly resilient network.
Extremely resilient. Reaching nearly 500,000 active nodes presents a massive surface area of potential compute.
But the text addresses why this specific network has a surplus of capacity in the first place. Because these nodes were originally deployed just to secure the Pi blockchain ledger.
Right, but the case study notes that the Pi ledger utilizes an energy-efficient consensus mechanism.
It doesn't rely on the computationally exhaustive proof-of-work algorithms like early blockchains did.
The ones that keep hardware running at maximum thermal limits just to validate blocks. That is a critical distinction to make. Because the underlying consensus protocol, which is likely a variant of Byzantine fault tolerance or federated Byzantine agreement, given their efficiency claims, requires minimal computational overhead to achieve distributed state agreement.
Meaning, the host machine's hardware is left largely unburdened.
Yes. The irony of early blockchain architecture was that it demanded maximum hardware utilization for zero external utility. It was just hashing math problems to secure the chain.
Burning electricity for nothing but security.
Right. But the Pi network's architecture secures the chain efficiently, which inadvertently leaves the vast majority of those 1 million CPUs completely idle, even while the node's software remains active and connected to the network.
So it creates this massive, latent pool of benign compute.
A sleeping giant, as you said.
The case study introduces the concept of utilizing this through decentralized cloud computing. The proposition is that third-party developers, specifically those needing massive parallel processing for AI, can tap into this distributed network.
And the node operators opt in to execute these external workloads, and they are compensated in cryptocurrency.
It is attempting to completely abstract away the complexity of hardware provisioning.
Exactly. In a traditional cloud environment like AWS, Google Cloud, or Azure, you are renting virtualized slices of localized, high-density hardware. You pay a massive premium for high availability and low latency within their specific data centers.
But decentralized cloud computing flips that infrastructure model on its head.
The cloud is completely atomized. The hardware is heterogeneous consumer-grade silicon spread across residential ISPs.
So the challenge for Pi is building the orchestration layer, the software that can take an intensive AI workload, chop it into asynchronous resilient microtasks, and distribute it across this highly volatile network of home computers.
Right, and the text explicitly states that these decentralized utilities run alongside existing node functions. They become a core component of the network's overall value proposition.
But raw CPU power, even a million cores of it, is really only part of the equation when we look at modern AI development pipelines. Because the case study pivots from purely mechanical compute to cognitive compute.
And this is where the case study really diverges from typical distributed computing projects like Folding at Home or BOINC. The Pi network is integrating a specific layer of verification that directly addresses a major bottleneck in AI training datasets.
Which moves us into Section 3, the secret weapon. The integration of KYC verification and the human in the loop.
Yes.
The case study highlights that the Pi network contains tens of millions of KYC identity-verified participants.
That's a staggering number.
It is, and these individuals can opt in to provide human-in-the-loop services for AI learning processes, and again, they get compensated via cryptocurrency.
We need to really examine the importance of KYC identity verified in this specific context.
Yeah, please explain that for you and me, because in the crypto space, KYC Know Your Customer is typically just discussed regarding regulatory compliance, right? Anti-money laundering.
Usually, yes. But in the context of distributed systems and artificial intelligence, it solves a massive technical problem: Sybil resistance.
A Sybil attack being when a single malicious actor spins up thousands of fake identities or fake nodes to overwhelm or manipulate a network.
Exactly. If you are crowdsourcing AI training data, your entire model can be poisoned if a botnet starts feeding it adversarial or just pure garbage data.
And the internet is increasingly synthetic.
Highly synthetic. As AI models scrape the web right now, they are increasingly ingesting data generated by other AI models. This leads to a recognized phenomenon known as model collapse.
The AI is eating its own tail.
Right. So high-quality, verified human data is becoming the absolute most scarce resource in machine learning.
By leveraging a network of tens of millions of users who have passed rigorous cryptographic and document-based identity verification, Pi is offering a highly Sybil-resistant pool of labor.
That's the key. An AI company utilizing this network has mathematical assurance that the feedback they're receiving is generated by a unique, discrete human being, not a generative script attempting to farm crypto rewards.
And the text specifies this is for human-in-the-loop support.
Yes.
So for you listening, this refers to processes like RLHF, reinforcement learning from human feedback.
Even the most advanced foundational models require human alignment. They need humans to rank outputs, label edge case images, or correct semantic logic.
So the Pi network is positioning itself as an integrated pipeline. The text notes they can offer a one-stop service to AI clients.
You have the latent CPU power of the nodes processing the raw, parallelized data sets. say, running massive amounts of image quantization or initial feature extraction.
And then, when the model encounters a low-confidence inference, something it doesn't understand, it can immediately route that specific data packet to the verified human layer of the network for cognitive resolution.
It beautifully bridges the mechanical and the cognitive.
I'm trying to picture this. So you have the node software running in the background on your PC. It's utilizing your CPU cycles to process tensor operations. Simultaneously, you might be sitting there and receive a prompt on your screen to manually verify a data point the model is struggling with.
Right. Is this a stop sign or a reflection of a stop sign?
Exactly. You
Yeah.
provide the cognitive baseline, your machine does the heavy lifting, and the decentralized ledger manages the microtransactions to compensate you for both your compute and your brain power.
If we connect this to the bigger picture, the socioeconomic claims in the text are highly ambitious.
Oh, absolutely.
The case study states this framework enables people to contribute to AI's production processes directly. Historically, human data, our browsing habits, our image captures, our text has been harvested as a free externality by centralized tech monopolies.
We've been the unpaid data labor for the entire AI boom.
We have. The proposition here is a structural reorganization of that economy. It shifts AI development from a purely capital-intensive model where you must buy billions in hardware to participate to an operational expense model distributed across the populace.
The users providing the underlying compute and the alignment data capture the financial value of their output natively via the blockchain.
It is a compelling theoretical architecture.
But the core of this document isn't just theory. They actually stress-tested this infrastructure.
Which brings us to Section 4, the OpenMind proof of concept.
Right. The case study details a pilot project executed last October with a partner company called OpenMind.
And OpenMind's specific focus dictates the really stringent technical requirements of this proof of concept.
The text describes OpenMind as developing an operating system and open-source protocol specifically designed for robots to think, learn, and work together. They use a fantastic descriptor here. They call it like Android OS for robots.
It is a very apt comparison. Before Android, mobile operating systems were highly fragmented and proprietary to the hardware manufacturer.
You couldn't run a Nokia app on a Motorola phone.
Right. Android provided an open foundational layer that abstracted the hardware, allowing developers to build applications that could run on a myriad of different devices.
So OpenMind aims to build the standard protocol for physical AI, providing the foundational spatial awareness, object recognition, and inter-device communication layers so that robotics manufacturers don't have to just constantly reinvent the wheel for every new piece of hardware.
But the text notes that developing this physical AI OS requires significant computing power to train, evaluate, and run their models.
We need to really delineate why physical AI, or embodied AI, requires a fundamentally different scale of compute compared to the large language models we are used to interacting with right now in our browsers.
Sure, an LLM operates in a highly constrained, tokenized digital environment. It is just processing text.
It's just predicting the next word.
Exactly. But physical AI involves a robot interacting with the stochastic, completely unpredictable physical world. This requires real-time, multimodal sensor fusion.
So a robot navigating a warehouse isn't just reading text. It is pulling in high-definition video feeds, LiDAR data, ultrasonic sensor readings.
And kinematic feedback from its own physical joints.
Right. It has to run simultaneous localization and mapping, or SLAM, while simultaneously running object detection and semantic segmentation on video streams just to understand its physical context.
It's incredibly heavy compute. And training these models requires exhaustively processing massive data sets of physical environments.
So the case study outlines how OpenMind utilized the Pi-node network to tackle a subset of this processing. They utilized container architecture to securely deploy their workloads onto volunteer Pi nodes.
Let's break down the mechanics of this container deployment, because security is the paramount concern when you are executing third-party code on untrusted consumer hardware.
Yeah, the text says OpenMind shared a container that requests computing tasks. So if I am a node operator, I am essentially allowing a robotics company to execute their code on my personal machine.
Which sounds scary.
It does. How does containerization prevent that code from accessing my local file system or compromising my OS?
Okay, so containerization utilizing technologies akin to Docker or Kubernetes fundamentally isolates the application execution environment from the host operating system.
Okay.
When a node operator downloads the OpenMind container, they are downloading a strictly defined, self-sufficient package. It contains the specific AI model, the runtime dependencies, and the system libraries needed for that specific task, and nothing else.
But it operates entirely within a sandbox.
Yes, the container engine on the host machine enforces strict resource limits. It dictates exactly how much CPU, memory, and network bandwidth the container is allowed to consume.
And crucially, it implements namespace isolation. The code running inside the OpenMind container has absolutely zero visibility into the host operating system's process tree, its network interfaces, or its file mounts unless explicitly permitted.
It is a zero-trust execution environment. OpenMind's container boots up, establishes a secure socket connection with its orchestration server, requests a payload of image data, runs the inference utilizing the host's isolated CPU cycles, and transmits the serialized output back.
The container cannot escape its sandbox, ensuring the node operator's privacy and system integrity remain completely uncompromised while they contribute to the network.
With that security architecture established, we should look at the specific task OpenMind executed inside these containers.
The case study states they were processing images using OpenMind's AI image recognition model to discover as many discrete objects as possible within these images.
This is a classic computer vision task, likely involving a convolutional neural network or a vision transformer optimized for object detection.
For a robot's OS to be functional, it must be able to parse a raw video frame into semantic objects.
It needs to identify a bounding box and assign a probability label to every relevant item in its field of view. People, vehicles, obstacles.
And doing this at scale requires running inference on millions of images. OpenMind took this workload, containerized the model, and pushed it to the Pi network edge nodes.
Which brings us to Section 5, analyzing the pilot metrics.
The text provides the exact latency and success metrics from this October pilot, but the first metric stands out immediately. The case study notes that 7 volunteer Pi node operators participated in this specific test.
And that number requires immediate contextualization.
It really does.
Yes.
Because we opened this discussion by noting Pi's aggregate network size of 421,000 nodes and over 1 million CPUs. To execute a proof of concept on merely 7 nodes seems counterintuitive. It raises the question, is this a statistically significant sample size to validate a global distributed compute network? So, what does this all mean?
While 7 nodes is a microscopic fraction of their total capacity, we have to look at what they were actually trying to prove with this pilot.
Okay.
In distributed systems engineering, testing raw throughput or maximum concurrent capacity is secondary to validating the orchestration and routing topology.
Getting the math done isn't the hard part.
The difficulty isn't getting a million computers to do math. The difficulty is the network fabric.
They were testing the plumbing, essentially. Validating the secure delivery of the container, the NAT traversal to communicate with nodes behind residential firewalls, and the asynchronous task queuing.
Precisely. If the routing protocol, the peer discovery mechanism, and the container isolation work flawlessly across 7 geographically disparate, heterogeneous nodes,
then scaling that to 7,000 or 70,000 is largely just a matter of load balancing and bandwidth provisioning.
Exactly. The critical metrics in this text are not the volume of compute, but the latency of the network execution.
So let's dissect those latency metrics. The text states, broadcasted jobs received acknowledgments from 7 workers within 1 second.
That 1-second acknowledgement is a highly significant metric.
Break down why.
Consider the network hops involved. OpenMind's centralized scheduler broadcasts a task manifest. That request traverses the public internet backbone, hits the ISP of the volunteer node, navigates through the residential router's NAT.
Which often aggressively blocks inbound connections.
Right. It reaches the Pi node daemon, is routed into the sandboxed container. The container evaluates its local resource availability, and then sends an HTTP or WebSocket acknowledgement back through that entire chain.
Achieving that handshake globally in under 1,000 milliseconds proves that the Pi network's peer-to-peer routing layer is exceptionally optimized for low-latency task distribution.
It demonstrates that the network is responsive enough for dynamic workload allocation. The system doesn't stall, waiting to see if a node is alive.
And the second metric is even more indicative of the hardware capability. The case study reports, inference results were returned from multiple workers within 4 seconds.
Let's break down the execution timeline of those 4 seconds.
Okay.
Once the node acknowledged the task, it had to download the image payload, load the image tensor into memory, execute the forward pass of the AI model against that tensor using the host's CPU, serialize the output data, and transmit it all the way back to OpenMind.
Doing all of that in under 4 seconds on a standard consumer CPU is deeply impressive.
It suggests OpenMind is likely using a heavily quantized model, perhaps an 8-bit or 4-bit integer model, specifically optimized for edge inference, rather than relying on high-precision floating-point operations that require massive GPU memory bandwidth.
It proves the viability of edge inference for heavy computer vision tasks.
If a residential node can return a complex object detection inference in 4 seconds, you can parallelize a dataset of 1 million images across 100,000 nodes and process the entire batch in seconds.
Rivaling the throughput of a centralized high-performance computing cluster, but without the localized energy concentration.
And the text details exactly what was in those results. The inferences weren't just simple binary classifications.
Right, the case study states the results contained correct object detections, including expected labels such as bus and person, along with bounding boxes.
The inclusion of bounding boxes confirms the complexity of the task.
It wasn't just a yes or no.
The node didn't just return a string saying bus present, it returned the exact spatial coordinates, the pixel parameters defining the location of the bus within the image frame.
Which requires significantly more compute and memory overhead than simple classification.
The case study summarizes these metrics by stating they confirm both distributed broadcast and result return path reliability.
The node successfully executed the untrusted code, performed the inference accurately, and the decentralized network successfully routed that granular spatial data back to the requester without packet loss or data corruption.
It validates the entire loop. It moves the concept of decentralized physical AI training from a theoretical white paper to a functioning, measurable pipeline.
Which brings us to the broader implications outlined in the final section of the text. Section 6 focuses on the future vision and this architecture as an alternative AI infrastructure.
The case study acknowledges the current state of the industry, noting that distributed AI training is still at the research stage in the world.
However, they position this successful OpenMind pilot as a tangible alternative infrastructure option for AI companies and startups. We are discussing a fundamental pivot in how AI infrastructure could be procured and deployed over the next decade.
It is a necessary pivot if we are to avoid a complete monopolization of the artificial intelligence sector.
The text explicitly links this distributed architecture to equitable participation and distribution. This is a direct counter to the current trajectory of the industry.
Right now, foundational AI development is a walled garden.
It really is. If you are a brilliant team of machine learning researchers with a novel architecture, but you don't have $500 million in venture capital to secure a multi-year lease on an H100 GPU cluster from a major cloud provider.
Your research is dead in the water. Compute is the ultimate gatekeeper.
This raises an important question regarding market dynamics. If the Pi network can successfully abstract the idle compute of 1 million consumer CPUs and combine it with the RLHF capabilities of tens of millions of KYC-verified humans, they are effectively building a decentralized, permissionless hyperscaler.
It allows a startup like OpenMind to bypass the traditional cloud oligopoly. They don't need to sign restrictive contracts or compete for scarce data center rack space.
They can write their container, fund an escrow smart contract with cryptocurrency, and instantly deploy their workload across a resilient global grid of edge devices.
It dramatically lowers the capital expenditure required to innovate in physical AI. Furthermore, it creates a robust, anti-fragile infrastructure.
A centralized data center is a single point of failure.
Exactly. A regional power grid failure, a cooling system malfunction, or a localized natural disaster can take an entire centralized training run offline.
But a distributed network spanning 421,000 nodes across multiple continents is inherently immune to localized disruptions. The network routing simply bypasses the offline nodes, ensuring continuous, resilient execution.
I want you to consider the reality of this architecture for a moment. The unused cycles on your personal processor, the machine sitting idle while you read an article or sleep, possess the aggregate capability to fundamentally map the physical world for autonomous agents.
Through protocols like the one detailed in this Pi network case study, your hardware is no longer just a depreciating consumer good. It becomes an active revenue-generating node in the global cognitive infrastructure.
It redefines the utility of consumer hardware. It shifts the paradigm from owning a terminal that accesses the cloud to owning a discrete unit of the cloud itself.
And that brings us to the conclusion of our deep dive. We have analyzed a truly dense and provocative case study today.
We examine the severe structural limitations of current AI infrastructure, the unsustainable energy concentration, and the algorithmic bottlenecks of highly centralized networks.
We explored the Pi network's architectural counterproposal, a globally distributed pool of over 1 million CPUs made available by the efficiency of their native consensus protocol.
We discussed the critical integration of KYC-verified human participants to provide Sybil-resistant, high-quality cognitive feedback.
And we rigorously analyzed the OpenMind proof of concept, where consumer nodes successfully executed containerized physical AI inferences, returning complex spatial data with sub-4-second latencies.
It is a compelling blueprint for a decentralized computational future. But as we synthesize this material, it demands that we reevaluate our relationship with the hardware we interact with daily.
How so?
Well, as AI developers increasingly rely on the latent capacity of our personal devices to process the complex sensor data required for robots to navigate our physical spaces, the strict demarcation between personal computer and global infrastructure begins to dissolve.
That's a wild thought.
If your laptop is secretly dreaming the thoughts of a robot on the other side of the world, whose infrastructure are we really building?
That is a staggering implication to consider. The line between our personal devices and the global AI architecture is thinner than we realize. Thank you for joining us on this deep dive into the Pi Network's decentralized computing case study. We hope this rigorous examination of edge compute, network latency, and physical AI infrastructure has provided you with a deeper understanding of where the industry is heading. Keep analyzing the systems around you, keep questioning the architecture of the tools you use, and we will see you on the next deep dive.